So last time we were seeing some of these identities for gradient operators. So today we will show this. So I'll just do maybe one or two examples more. But once you get the idea, then I think you can derive many of these identities on your own. So today I will show you this particular identity: del cross u cross v is del u times v plus del dot v times u minus del dot u times v minus del v times u. So again, so you write your del cross u cross v as equal to epsilon ijk, epsilon ijk. So let me write the ith component of this. So that is times del j, you can write, and then maybe u cross v k component. So this will be equal to epsilon ijk. Then this I will write as epsilon k mn um vn. And then this can be put outside, so this will be epsilon ijk, epsilon mnk, and then this you can write as del by del xj of vn. Okay. And now again use the epsilon delta identity, so this will become delta im delta jn minus delta in delta jn times del um by del xj times times vn plus um times del vn by del xj. And then, so just expand this out using the product rule as I've shown here. Now use the substitution operator property. So you'll get that this is equal to Vj times del ui by del xj plus ui times del vj by del xj plus minus vi times del uj by del xj minus uj del vi by del xj. And then now this you can so you can see this del ui by del xj. So del u, the ij component, is equal to del ui by del xj. So you can write it as this matrix, del u matrix, multiplying the vector v. So that will give you, so suppose if I multiply now del u times v, the ith component, so that will give me del ui by del xj times vj. And so that is this particular term. So that is this here. So that is this del u times v. So let me just write it out here. So this whole thing is now del u times v plus del dot v times u minus del dot u times v minus del v times u. The ith component of all of this. So we started out with the ith component of this, and then we got the ith component of this one. So both these things are equal. Okay, so this is how you would derive many of these identities. So I think you have got an idea. So probably we will not derive any further identities. I think you can look at the book for some more identities or some of the previous assignments or tests, and then you can try to derive some of the identities in that. Fine. Now we'll go to the next topic, which is the Gauss divergence theorem. Okay, so this is a very important theorem. Okay, the divergence theorem, and so we will use it extensively at a later stage. Divergence theorem. So if P is a scalar field, if P of x comma t is a scalar valued field. So, for example, a scalar valued field could be temperature or density or so on. Okay, so that's a scalar valued field. Then integral of del phi times dv is equal to integral of p times n times ds over s. So this is over p. So suppose if p is the volume, the domain of over which this p of x of t is defined, and s is now the closed surface, okay, of this domain p, then the divergence of p over p is equal to p times n. So this n is the unit normal to this s. So this is, as I said, this is very, very useful for converting from volume to surface integrals and from surface integrals to volume integrals. And so we will use this theorem very, very extensively. So one recipe, okay, that I will give here at this particular stage is that del by del xi goes to ni. So this is the, this is just a recipe. This is not a proof of the Gauss divergence theorem. So, for example, here your this del phi is nothing but del phi by del xi, right? The I component of this is del phi by del xi. So the del by del xi goes to ni, right? So this goes to p times ni. So this, as I said, that this is just a shortcut for remembering this particular relation. It is not a proof. So the proof for the Gauss divergence theorem is quite complicated. So we will not go into the proof of the Gauss divergence theorem. But I am just telling you how to use the Gauss divergence theorem. So basically you have to use this particular relation here that I have shown. So let me give you another example by which this will become clear. So suppose if I wanted to write the Gauss divergence theorem for del dot u. So del dot u times dv over v. Then now what we get is that we will get u dot n times ds over s. This so this del dot u can be written as del ui by del xi, right? Because u is a vector in this particular case. So I am putting the tilde below that to indicate that it is a vector. Now this del by del xi goes to ni, correct? So this goes to ui ni, correct? And ui ni is nothing but u dot n. So this way you can generate the results for lots of other cases also. So as I said, let me just give one more example. So suppose if you wanted del dot t, that is e the second order tensor v, then this will become integral of p times n times ds over s. So here your del dot t, the ith component, so del dot t, the ith component is del t ij by del xj. Now this del by del xj goes to nj. So del by del xj goes to nj. And so this will become t ij nj. So you will get t ij nj. And so that that's the ith component of t times n. Okay, so del dot t will go to tn times ds. So as I said that we will not go. This way you can keep generating, but we will not go into all the possible cases. But if you remember this fundamental rule here, that del by del xi goes to ni, then I think you can easily generate results on your own for this Gauss divergence theorem. So as I said, we will use this extensively while deriving various kinds of equations here. Fine. Then there is another theorem, which is the Stokes theorem. So we'll get that also. But for the Stokes theorem, actually we will not use it so extensively, but just so Stokes theorem. So So let C be a contour. C be a contour, and S be any area. The area, sorry, the area of an arbitrary surface, the surface enclosed by C, then integral or the contour of u dot dx equal to del cross u dot n times u. So let me just draw this contour. So this is your contour C, and now you can think of that this is some surface. So this is in 3D. You can think about it. That let's say, suppose you can consider that this is a hemisphere or something, and so if you take a tennis ball and you cut it, right? So at the equator or something. So that whenever you are cutting it, that part will be C, and then the top portion of the ball, right, that will be your S. So the N again is the unit normal. And this unit normal to this. So u dot dx. Now this dx is an element of length along the contour. So this u dot dx is along this dx. So that is equal to del cross u dot n ds over s. So that's one of the things. And then similarly, you also have u cross dx is equal to this over c. So this is integral of del dot u times n minus del u transpose times n the whole times ds. So this particular set of theorems, actually we will not be using it much, but probably you may use this particular theorem in fluid mechanics, because the circulation will be defined in this particular way. U will be the velocity vector in that case, and so the circulation will be defined, and then this will be the vorticity vector. Del cross U will be the vorticity vector. So here, at least in solid mechanics, we will not use these relations. So more, the Gauss-Divergence theorem will be more useful for our applications. Then the next result is what is known as the localization theorem. Again, this is a very, very important result. So let me just state that. So localization theorem. So let P be a continuous scalar vector or tensor valued field, tensor valued field on B domain, and then takes integral of C d over B equal to 0 for all B, then B is equal to 0. Okay, so this is, you have to be very careful how you interpret this. So here, for all V, okay, so this is very, very important. So what we are doing is that suppose you take some domain V, okay, and now this V of dV is 0 over this V. And then similarly, now if I take any other subset of this, and now you take that as V, or you take some other domain and that is V. So for all possible collections of the domains V, so that is what we mean by for all V. So if V dV is equal to 0 for all V, then V itself is equal to 0. Okay? So this is very, very important. Okay, that for all V is very, very important, because even a one-dimensional example, so if the domain is fixed, then obviously this is not true, right? So just if you take the sine function, right? If you just take a sine function, then or from 0 to 2 pi, you will see that the integral is 0, but the integrand is not 0. So here in this particular example, now if I apply this that for all v, so you can think that suppose if I choose now this as v, okay, so now here the integral is not 0, so here suppose the function has to come down to 0, and now you think about it like this. Now I choose another v, okay, so then I will choose this as my v now. Then now again this function, the integral has to be 0, correct? So that means this function cannot be like this. So again you can think that this function also comes down to 0 and so on. So wherever it is positive or negative, I will choose that portion as my v. So this is just a rough idea of the proof. Okay, so the actual proof again is a little bit complicated, but I am just trying to give you sort of intuitive version of why this theorem holds. Okay, so basically you are using this arbitrariness of v to show that the integrand is 0 everywhere. So that's the idea. So this again will be very, very useful theorem. So basically we will see at a later stage that all the balance laws that we will write, right? Balance of mass, balance of linear momentum, balance of angular momentum, or whatever, any balance law that we will write will be an integral form. Okay, so that will be written over what is known as a material volume. So at this stage, do not worry about what this material volume is. Then we will say that the material volume is arbitrary, and then from that we will deduce the differential equation form of the Terney equations. Okay, so the differential equation form will be the integrand of that particular integral. So because the integral is 0 and because the domain is arbitrary, the integrand, which will be the differential equation, will be equal to 0. Okay, so that is how we will derive the differential equation form starting from the integral form of the equation at a later stage. Okay, so at this stage, as I said, don't worry about it, but you should just understand what this theorem is saying. Okay, then I think this sort of completes the portion for the assignment. Okay, so you can now proceed, because now I think that all the material that is required for your assignment is completed. But in the tensor part, I just wanted to do one additional part which I had skipped at that time, but I think it is an important thing, so let me just mention that. That is to do with symmetric positive definite tensors. So I never defined the, I defined what is symmetric tensors, but I did not define what is meant by positive definite tensors. So I just wanted to do that a little bit briefly. So let's just get that. So a tensor S, right? Tensor S belonging to sim. So sim is the set of symmetric tensors. Is said to be positive definite. Is said to be positive definite if U, SU is greater than or equal to 0 for all U belonging to V, and is equal to 0 U, SU with U, SU equal to 0 if and only if U is equal to 0. So this is the, so basically if you take some non-zero U, okay, then this and if S is positive definite, then U, SU is always strictly greater than 0. So this equality is achieved if and only if U itself is 0. So this is the definition of a positive definite symmetric tensor. Positive semi-definite is if it is greater than or equal to 0, but this equality can be 0, but you do not have this if and only if U is equal to 0. So basically, you can have that is equal to 0 or some non-zero U also. So then in that particular case, you will say that it is positive semi-definite. Okay? So this is the definition of positive definite symmetric tensor. So actually, why is it that we define positive definiteness only for symmetric tensors? What about, so why can't I say positive definite arbitrary tensor? So for that, let us just look at an arbitrary tensor. tensor. So you can see that T is equal to T symmetric plus T skew symmetric, right? So this is the decomposition that we had looked at. Now, if I write U comma TU, right? So this will become U comma TS of U plus U comma T skew symmetric of U. So this is just I have used this particular decomposition and then I have substituted it here. Now you will see that this U comma T skew symmetric U is equal to 0, right? So that is we have shown that for skew. So if you recall, I have shown that U comma WU is equal to 0 in one of the previous lectures. I think probably the last lecture we showed this. So the proof for this was just use the W transpose, right? So this is actually W transpose U comma U, and then that is equal to minus of W minus of WU comma U, and so WU comma WU is minus of WU comma U, and so hence it is equal to 0. Right? So that proof we have shown. So basically what happens is that this part goes to 0, right? U comma TS. So you can see from this that even if I consider an arbitrary tensor, right, the positive definiteness is decided only by its symmetric part. So the anti-symmetric part plays no role in deciding whether a tensor is positive definite or not. So that is why actually whenever you see any matrix algebra book or linear algebra book, they will always talk about positive definiteness of symmetric tensors or symmetric matrices only. They will not talk about positive definiteness of arbitrary matrices. That is, the reason is here that finally only the symmetric part decides whether a matrix or a tensor is positive definite or not. Okay, then now let us look at some of the characterizations of a positive definite symmetric tensor. So let me just write it here. So we have this following theorem here. So so the following are equivalent. So I will write it as TFAE. So this TFAE stands for the following are equivalent. Okay. So one is that S is positive definite. And two is that the eigenvalues lambda I, are all greater than 0. So that means I equal to 1 to 3. I equal to 1 to 3. All the three eigenvalues are greater than 0. Okay. Third thing is that the principal invariants are also greater than 0. So the principal invariants that is I are greater than 0. So that is I1, I2, I3. That is the trace will be greater than 0, determinant will be greater than 0, and the second principal invariant will also be greater than 0. So let us, I will not prove the entire theorem, but I will prove maybe one or two of these implications. So, so the reason actually I am doing this is that you will see how important the spectral decomposition. So this is one very, very important application of the spectral decomposition. See, last time I told you that for proving any theoretical property of symmetric tensors, the spectral decomposition is critical. Okay, so this is one very nice example. So if you try to prove this theorem without using the spectral decomposition, you will see that that is very, very difficult. Okay, so let us just try to show this. So S now I will write it as Si Ei star divided Ei star. So this was the spectral decomposition that I derived the last time. So from this you can write Su is summation lambda I Ei star and U dot Ei star. U dot Ei star. So this I will call as Ui star itself. So this is equal to summation of lambda I Ui star Ei star. And then if I write U comma Su, so this implies that U comma Su, so take the dot product of this with U, so again U dot Ei star will again give another Ui star. So this will be equal to summation of lambda I Ui star square. So remember we have to put the summation sign because otherwise the summation convention will get violated. So I am writing the summation sign in this particular case here. So this is from I equal to 1 to 3. I equal to 1, 2, 3. Now let us try to show some of these results here. So first is that if it is positive definite, then the eigenvalues lambda I are greater than 0. Right? So here, so suppose let us write the eigenvalue problem. Right? So Sn is equal to lambda n. Right? This is the eigenvalue problem. Right? Now you can from this, if you take the dot product on both sides with n, see everything is here because we have already shown, so we don't need to worry about complex values and so on. Because for a symmetric tensor, we have already shown that the eigenvalues are real and the corresponding eigenvectors are also real. So lambda I can write as n comma Sn, right? Because that is just take the dot product on both sides and your eigenvector is normalized so that the magnitude is 1, so you will get n comma Sn. Right? So now by the definition of the positive definiteness, n is a non-zero vector, hence n comma Sn will be greater than 0 since S is positive definite. Right? So since S is belonging to P sim, so this P sim is positive definite symmetric tensors. Okay, so this is the notation that I will use. So the lambda will be greater than 0. So similarly for all n, I mean for all lambda, that lambda 1, lambda 2, lambda 3, all of them will be greater than 0. Okay. Now conversely, you want to show that if the lambda i's are greater than 0, then u comma su is greater than 0. So basically now let us look at this particular object here. This is this u comma su. So now you are given, so now given, so conversely now. So conversely given that lambda I are greater than 0, right? Then, so that means all the three eigenvalues are greater than 0, right? Then you can see that this is always going to be greater than 0, right? Because so if you take a non-trivial u, right, then you can see that this, because now the lambda are greater than 0, this is also positive, so the sum of positive numbers, so u comma su is going to be greater than 0. So then let us call this as star. So from star, star, you will get that u comma su is greater than 0 if u not equal to 0. Right? And you also have to show that it is equal to 0 if and only if u is equal to 0. So you should not forget that particular part. Okay? So that also we need to show. So let us show it here. Yes, so if I need to show that, so suppose if u is equal to 0, right? If u is equal to 0, then that implies that ui star is equal to 0. Correct? And then from there, you will get that u comma su is equal to 0. So that is obvious. Now conversely, if u comma su is equal to 0, right, then that means, so conversely, if u comma su is equal to 0, then now that summation of lambda I ui star square is equal to 0. And now lambda I is positive, right? And this also has to be equal to 0 then, because you cannot get, so suppose if it is non-zero, then this cannot be equal to 0. Right? So this will imply that ui star has to be equal to 0, right? Because lambda is a positive. So since lambda I is greater than 0. So that's the reason. So and so then the vector will be 0, because if all the components are 0, then the vector itself will be 0. So that is how you show that if S is positive definite, then all the eigenvalues are positive. If all eigenvalues are positive, then the symmetric tensor S is positive. So if it is positive semi-definite, okay, then the eigenvalues will be non-negative. Non-negative means some of them can be 0 and the remaining ones can be positive. Okay, so that is what we mean by semi-definite. So that it will be a combination of some 0 eigenvalues and some positive eigenvalues, but they cannot be negative. So what we mean by non-negative means they cannot be negative. In that case, if it is positive, semi-definite. Okay? And if it is positive definite, then all the eigenvalues have to be strictly positive. So I hope that difference is very clear. And then I will not show the second implies third implication. So if suppose if lambda I is greater than 0, then you can see that I1 is equal to lambda 1 plus lambda 2 plus lambda 3, so that will be greater than 0. And then I2, which is equal to lambda 1 lambda 2 plus lambda 2 lambda 3 plus lambda 1 lambda 3 is also greater than 0. And then your I3, which is equal to lambda 1 lambda 2 lambda 3 is also greater than 0. So now what we have shown is that if the tensor is positive definite, then the eigenvalues are positive and hence the principal invariants are also greater than 0. Now conversely, if the principal invariants are greater than 0, then actually the eigenvalues are also greater than 0. So that proof I will not get into. That is slightly complicated, not very complicated. So try to show it on your own, then you will realize how difficult some of these proofs are. That's the reason I am not doing it. So now basically you are given that I1 is greater than 0, I2 is greater than 0 and I3 is greater than 0. And now you need to show that lambda 1, lambda 2, lambda 3 are greater than 0. Okay, so you will see that it's a very non-trivial proof. So I think it will be a nice challenge for you people to try and prove this. As you can see, it's going to be very non-trivial. But if you look at the book, so what I would suggest is don't look at the book in the beginning, try to prove it on your own. But you will see that in the book there is a very, very elegant proof. Okay? So anyway, we will not get into that at this particular stage here. So actually this sort of completes the first chapter of the book. Okay, so because as I said that we are not going to go into very detailed proofs about the other aspects of tensor analysis and so on. Okay, so what we are going to do is that actually I am not going to start a new topic, which is the kinematics. So that I think because that requires a much more detailed study, so that I will leave it for the next time. Okay, so the next class. So only one thing is that whenever there is a holiday, Mondays and Fridays, so that time we will not record. But tomorrow's difficulty session we will have live. Okay, fine. Okay, yeah, fine. Okay, so actually, I think we have enough time here today. So maybe, yeah, what he's saying is correct. So today we will just start maybe with kinematics actually. So this. Okay, so let us start with kinematics. So kinematics is actually the branch where things depend only on the geometry. Okay, so that means we will define objects such as strain, for example, right? So that is just a purely geometrical concept, right? In your strength of materials, you have learned. I mean, you have probably learned just a very rough idea of strain, that is just change in length per unit length, things like that, right? So it depends only on geometry. So it doesn't talk about, for example, it doesn't talk about what are the forces that are acting on the body to produce that strain. Okay, so this kinematics refers to such geometrical concepts. Okay, so in fluid mechanics you will come across the rate of deformation tensor. Okay, so or actually there in fluid mechanics they will refer to that as rate of strain tensor. So that is also a kinematical quantity because that is just the gradient of the velocity and so on. So that actually you will learn in your fluid mechanics course. Right now don't worry about that, but I'm just mentioning that these are kinematical concepts. So kinematical means that just geometry based. So kinematics, so just based on geometry. Geometry alone. So that means we do not bring in forces here. So let us look at now a typical deformation. Okay, so that is, suppose now let us fix one coordinate system here. So this is x1, x2, x3, or let me call it E1, E2. That will be better. E1, E2, E3 are the basis vectors. So imagine that this is just a Cartesian coordinate system that I am setting up. Now you imagine that there is some body. Okay, here this is some body, and now it is getting deformed to some other shape due to some application of forces. But at this stage, as I said, we will not consider what the forces that are acting on this particular thing are. So let us take that some point in the, so this I will call as a reference configuration. Reference configuration. And this here, so it undergoes some deformation, and then whatever new configuration that it achieves, I will call it as the deformed configuration. Okay, so if you take a typical point X in this reference configuration, then that goes to some position vector small x in the deformed configuration. Okay? And then this difference between the deformed and the undeformed configurations we will call as U. So U will now denote the displacement vector. So this, so the your displacement vector is U is equal to small x minus x. Okay, I mean, just to give you a concrete example of what we mean by the reference configuration and the deformed configuration, so let me just draw one configuration like this. So suppose you imagine that there is a cantilever beam, right, and then there is some load that is acting on your cantilever beam. Okay, so now before the application of the load, right, it is in this horizontal position. So this would be your V0. Suppose if I call this as V0, and this I will call as V of t. Right? So it is continuously deforming in position. So this would be your V0. That is the configuration before the application of the forces would be V0. And then now you apply the load. Now it goes to some deformed position like this. Right? So now let us call it so this one. Right? Now this is your V of t. After the application of the force, whatever is the deformed configuration, that will be V of t. So this is a yes. Yes, so let us see. So this capital X is known as the X and small x are known as the material coordinates, and the small x are known as the spatial coordinates. Yes. And so we will assume that there is a continuous mapping from this capital X to small x. So, okay, so just one point about the notation. Typically, I have said that I will denote vectors by lowercase letters, and I will denote tensors by uppercase letters. But this is an exception. So this capital X is actually a vector, that is just the position vector of a point in the reference configuration, and the small x is the position vector in the deformed configuration. So I am using a capital X, although that is a vector. So this will be probably the only exception, but the reason that I am using this particular notation is because this is what is widely used in the literature. Okay? So later on you will have to read some books or papers, and they will be using this particular notation. So that is the reason that I am making this particular exception to this rule that capital uppercase letters or capital letters will be tensors. So in this case, this X just denotes a position vector of a point in the reference configuration here. Fine, then we will assume now that there is a one-to-one mapping. So assume that there is a one-to-one mapping, and there is a one-to-one mapping that takes capital X to small x. Okay, so that means I will write this x as equal to pi of x of t. So this pi, okay, so this is the symbol pi. This is like a function. Okay, so it takes capital X and then t is just the time. So it takes this capital X comma t and it maps it to the position vector of that particular point in the deformed configuration. So that is this model. So we assume that it is 1 to 1. So what that means is that so we do not assume that suppose there are 2 points in the reference configuration, they will not go to the same point. So suppose if this is x1 and this is x2, they will not go to the same x. Okay, so that is an assumption that we are making. Actually, this assumption can be violated. So if you take, suppose if you take a flexible bar and then you bend it, and then what happens is that, and then you touch it, right? So then the 2 points at the extremities will come and they will join, right? So if you just bend it and allow them to join in this way. So, but that is only on the surface, right? So typically we will consider only points within the domain, right? For this, so that is the reason that exception we will allow in the sense that so when I am talking of this 1 to 1, typically I am referring to points within the domain, not on the surface. So we will assume this, and also the other thing is that suppose if you have a point x, then it cannot split and go into 2 different positions. So that is what we mean by 1 to 1 mapping. So basically, the implication of this 1 to 1 mapping is that I can invert this particular relation, and I can go from small x to capital X also. Correct? So because it's a 1 to 1 mapping, so I will also have that x can be written. So x can be written as pi inverse of x comma t. So this is some inverse mapping. So what you have to remember is that this is a vector mapping. Okay, so that means if I write it in slightly more detail, just write that. So what this means is that your x1 is equal to pi 1 of x1, x2, x3, t. And your x2 is equal to pi 2 of x1, x2, x3, t. So this, I'm just writing it out in a slightly more elaborate form so that you understand. So this is a vector mapping. Okay, so this, when I put a tilde below that, that means it's a vector. Right? x3 is also pi 3 of x1, x2, x3, comma t. And so similarly, this will also be, the inverse will also be a vector mapping. So that means it will be pi 1 inverse of x1, x2, x3, comma t. That will give you capital X1, and similarly for x2 and x3. So this whole thing is like a motion, right? So which goes from the reference configuration to some deformed configuration. Okay, then the formulation in terms of capital X is called as Lagrangian formulation. So in terms of X, so let me rewrite it here. So formulation in terms of capital X, formulation in terms of capital X will be known as Lagrangian formulation. Lagrangian formulation, and formulation in terms of small x. So formulation in terms of small x is known as an Eulerian formulation. So in honor of Lagrange and Euler, right, they were mathematicians, applied mathematicians who did very pioneering work in the field of mechanics, right? I mean, all the mechanics that we are learning today is primarily due to the work of starting from Newton, then Lagrange, Euler, Cauchy, and so on and so forth. Okay, lots of scientists, but primarily done, let's say, in the 17th, 18th, 19th century, right? So that is primarily that stuff. So this Euler, Lagrangian and Eulerian are coming from Lagrange and Euler. Typically, problems in solid mechanics will be in the Lagrangian formulation, and problems in fluid mechanics typically will be in the Eulerian formulation. So I think these details we will discuss in the next class.